Activation function is the final step before you assign the value of the neuron. The calculation process is done by multiplying the values of the previous layer's neurons with the corresponding weights and then sum up with the bias. As you can see in the equation, the value z is then taken and goes through the activation function f. Activation function f returns the value a, which will be the final answer for the neuron's value. You will get answers to all your questions about activation functions in this video. We already answered what are activation functions, and in the next minutes of the video you will know why do we use them, why there are different types of activation functions, and which one is best to use. Let's continue with the question why do we use them. Well, the short answer is nonlinearity. We need nonlinearity in our neural network, so we use activation functions. Now let's break down what this nonlinearity means. Let's refer back to our equation where we calculate z value and then we use activation function to get a value. Now let's say we don't have activation function f, so our equation will only be the calculation of z value. Now if you pay attention to this equation, you will see that this is identical to the equation of linear regression. So if you remove activation functions, your neural network will basically be multiple layers of linear regression. But we don't want this to happen. We want more advanced model to solve more advanced problems, such as NLP, image recognition, pattern recognition, and so on. That's why we need to use activation function in order to have better model than simple linear regression. That's why activation function is introduced to have nonlinearity in our model, so the model can learn nonlinear properties of the dataset. So as we know why do we use activation functions, now let's move to why there are different types of them and what is their advantages and disadvantages. We will start with sigmoid or logistic function. This is the graph of the sigmoid, and as you can see, it takes any value and maps it to the range between 0 and 1. This looks like probability because it takes any value and returns a value between 0 and 1. For example, if it returns 0.8, it means 80% probability. So this is mainly used in the final layer of classification problems where you need probability as the answer of your model. For example, if you get 0.6, it means this image is 60% cat. Sigmoid function was mainly used in hidden layers in the first years of neural networks. But then a problem called vanishing gradient happened, and the models needed a more advanced, a better activation function to solve this vanishing gradient problem. But before moving to that activation function, let's see what this problem means. I want to quickly mention that I have written a Medium blog about activation functions. You can get the link from the description and check out the blog. Vanishing gradient problem happens during backpropagation. During backpropagation problem, in order to update weights, we need to multiply by the derivative of activation function in every layer. And here you can see derivative of sigmoid function, which is the blue graph, and the maximum value is 0.25. And usually it's not that high value, it can be in these areas between 0 and 0.2. And when you multiply by this small number over and over again, the gradient becomes very small number. So it doesn't update the weight significantly, and the learning process gets stuck. When vanishing gradient problem happens, it means the gradient becomes very small, it vanishes, and the learning process doesn't continue. In order to solve this problem, the applied activation function is ReLU. This is graph and equation of the ReLU. The ReLU returns the positive values as they are, it doesn't apply any calculation, and it returns 0 for negative values. This process has been formalized with this equation of maximum of 0 and x value. When the x value is negative, the maximum will be 0 and 0 will be returned. When the x value is positive, the value itself will be returned. ReLU solves vanishing gradient problem, but it has another problem called dying ReLU problem. Now let's see what this means. When you have many negative values in your input, the ReLU will map all of them to 0. And you will have many neurons with the value of 0. So you will not have enough active neurons in order to get learning process. So we know that why dying ReLU problem happens, which was because of negative values. Let's see how we can solve this. The next activation function is Leaky ReLU, which is an advanced version of ReLU, and here the equation has been modified. In ReLU, the negative values was returned as zeros, but here it has been returned as a very small negative number. As you can see here, the graph is not exactly zero. I have plotted with the value of 0.05 for better view. With Leaky ReLU, negative values will not be zero anymore, so the dying ReLU problem will not happen. The next activation function here is Tanh. Tanh looks like Sigmoid, but it has a range of -1 to 1. This activation function also has vanishing gradient problem, that's why it's not preferred anymore, but it can be used instead of Sigmoid in the situations where you need negative values as well. In the final source, I want to mention that nowadays in many neural networks, ReLU activation function or its modified versions such as Leaky ReLU are used. These activation functions are prone to vanishing gradient problem. This activation function works very well in many situations, so you can start your neural networks by using ReLU activation function, and then you can apply different activation functions for hyperparameter tuning. So we answered all of these questions in this video. If in the notebook provided in my GitHub page, you can find different functions in Python. Starting with the sigmoid, we have here the equation of sigmoid, and it has been plotted with the range of -7 to 7 with 200 values. And here we have plotted its function. As you can see, it's between 0 and 1. All the plots have been plotted using NumPy and matplotlib libraries. Secondly, we move to ReLU. Here we have its function as well. It's the maximum of 0 and x. And here we have plotted it. As you can see, it's 0 for negative values and the value itself for positive values. The next one is Leaky ReLU. Here you can change the alpha parameter and you multiply alpha by x instead of 0 in the ReLU. Let's specify the difference. As you can see here, it's 0 and x, but in Leaky ReLU it's alpha times x and x. Again, we have the graph, and with the alpha value, the slope here changes. After that, we have Tanh function. The difference with sigmoid is that it has the range from -1 to 1 instead of 0 to 1, and in the graph it has been shown clearly. The next step is sigmoid and its derivative. As you can see, we have here sigmoid function itself again, and then its derivative. Both of them have been plotted in the same graph. The orange one is the sigmoid and the blue one is derivative. The maximum value of derivative is 0.25, so it's a very small number. When you multiply by the derivative of sigmoid over and over again, the gradient becomes very small and vanishes, and the learning process gets stuck. Even if it's 0.25, it's not usually the highest value, of course. If it's lower value, it's even more problem. Again, you can check out my blog for reading if you like to read the topic rather than watching a video. You can find details and all the explanations here. You can check my blog in Medium, which I have written about activation function, and the link will be in the description. Also, you can check the code in GitHub to see different activation functions in Python. See you in the next videos.